Our first of two models today is going to be something called the logistic model. Now, wait a minute. Didn't we discuss the logistic model before? Yes, we did. We were talking about the logistic model before in the context of iterating functions. And that was where we were discussing the period doubling root to chaos and that kind of thing. But this is different. This is the logistic model for differential equations. For ODEs is another abbreviation people use for ordinary differential equations. We're going to let Y be the population of, just to be something specific, say fish in some lake, maybe fish in White Bear Lake. What noise is that? Do you hear that noise? Something's going on in the building here. Fish in White Bear Lake, Minnesota here, and that it's not only a town, it's also a lake. A function of time. So that's your dependent variable, this population. And probably to make it simple, you'd want to use units of like maybe millions of fish. I mean, White Bear Lake's pretty big. I'm pretty sure there's probably over 1 million fish in there. Say in millions of fish. And maybe it'd be better to focus on one species, but I won't bother making it more complicated that way. That's our dependent variable. And then T is time, maybe in years, since the beginning of the current year, which is 2023, since January 1st, 2023. All right, so those are our variables. Are there some parameters? What do I mean by parameters? Like, well, something related to perhaps the growth rate of the fish, how fast they reproduce, or how fast they die. And maybe also something related to the fact that the lake is limited in size. It's a fairly big lake, but it is a finite lake. I'm going to let K be a parameter representing well, you could call it the continuous growth rate when the population is small. Continuous growth rate for small populations, like close to 0. And maybe L for a limiting value on the number of fish, often called the carrying capacity of the lake. Carrying capacity. We talked about that in the context of the discrete logistic model as well. And we saw in the discrete logistic model, not only did chaos sometimes happen, but sometimes the population actually overshot the carrying capacity before it went back down again. Does that happen with differential equations? We're going to have to explore and find out. So what is the differential equation here? dy dt giving you the rate of change of the population with respect to time. It is going to be a first order equation just involving the first derivative of y with respect to t. If it were an exponential growth model, then dy dt would just be k times y. But wait a minute, this is not an exponential growth model. It's something different. So why did I write k times y? Well, it's still part of the model. I would like to now multiply this by something that is close to 1 when y is small, implying that the growth is close to exponential when y is small. Wouldn't that make sense? If this is an exponential growth model, and I multiply it by something that's close to 1 when y is small, it should still be an exponential growth model when y is small. But then, as y gets bigger, as the population grows, I want dy dt to decrease to 0, I guess, so that the population levels off, perhaps. So I'd like to multiply also by something that's close to 0 when y is close to L. And the simplest kinds of things you can think of here are, well, you could do L minus y as one option. A little bit more common is to do 1 minus y over L. 1 minus y over L. That is a quantity that is close to 1 when y is close to 0. when y is small compared to L, especially. Right? That'd be close to 1 when y is close to 0. And it's close to 0 when y is close to L. In fact, it equals 0 when y equals L, implying that the horizontal line y equals L would be an equilibrium solution. The constant function where y is always equal to L for all time would make this quantity 0, no matter what t is. And, well, yeah, constant functions have derivatives that are always equal to 0. So dy dt would also always be equal to 0. But obviously, there must be other solutions as well. Let's add in a generic initial condition, y of 0 equals y sub 0, and we're off. Let's try to solve it. Oh, it doesn't look so easy, does it? Can we separate variables? Should we separate variables? Yeah, we can. This is solvable, and we will solve it right now. It's not as easy as some of the other ones we separated variables for. What are we trying to separate? We're trying to separate the y and the t, not the k and the l. Those are constants. I'm going to divide both sides by everything that involves y. In fact, essentially divide everything by y times 1 minus y over L. And pretend like I'm multiplying everything by dt, even though that's not literally what's going on. I'm really just rewriting the differential equation in an equivalent form, pretending that I'm multiplying both sides by dt and writing the differential equation in this form. And this is where we get the urge to integrate both sides, and that is a good idea. But maybe before I integrate both sides, maybe I don't like the fractions within fractions here, so maybe I should multiply the top and the bottom of this fraction by L dy over, and then distribute the L through the parentheses down here, like that. I changed the function on the left side, its form. It's still equivalent because I multiplied by 1 in the end, L over L, leaving an L on the top and distributing the L through the parentheses there, leaving this on the bottom. And now integrate both sides. That's a little nicer. Right side's easy. K is a constant. Kt plus some constant of integration, call it C1. Right side is harder, but you did do this in Calc 2. Maybe in DiffyQ as well. How do you integrate something like that? Here's a little hint. Partial fractions. You want to break that fraction apart into pieces. Solve for a and b where this is true. You will be able to do it. There are two values of a and b that will make this equality true for all y, where these functions are defined, which means we don't include y equals 0 or y equals L. However, it's a little funny in solving for a and b. I'm going to use the values of the resulting expressions after multiplication by the common denominator at y equals 0 and y equals L. So what did I do to get from here to here? I just multiplied by the common denominator of y times L minus y, getting complete cancellation on the left, just an L, complete cancellation of the bottom, partial cancellation of the bottoms on the right. Again, make a note to yourself if it's helpful. I multiplied both sides by y times L minus y. Multiplying that one by y times L minus y cancels the y's, leaving you with this. Multiplying this one by y times L minus y cancels the L minus y's, leaving you with this. Now, yes, plug in y equals 0 and y equals L to help you solve for a and b. It's a little funny because technically this expression is undefined when y is 0 or when y is L. But with this one, I'm about to plug in y equals 0 and y equals L to solve for a and b, and it turns out to still give you the right answer anyway. Just a little trick, save a little time. Y equals 0, plug it in and get L equals a times L plus b times 0. implying a equals 1. Plug in y equals L, and you get L is a times 0 plus b times L, implying b is also 1. So that means this integral is the same as this integral. As a way to check it, you could always add these fractions and simplify. And if you do, you can check it. You will get this function here. And this integral is easy to do. Natural log of the absolute value of y. Careful though, minus the natural log of the absolute value of L minus y. Why is there a minus sign there? There's a minus sign there, that's why. If you thought about doing the integral of 1 over L minus y with a substitution, like w equals L minus y, dw would be negative dy. Another way to check that you need a minus sign there is to differentiate this. The chain rule would give you an extra factor of -1. And by property of logarithms, that's the same as ln of the absolute value of y over the absolute value of L minus y, which is also the same as the ln of the absolute value of y over L minus y. I'm putting extra parentheses in there that most people don't bother with, but that's okay. So we've got this thing equals this thing. What are we trying to do? We're trying to solve for y. Get rid of the natural log first by exponentiation. Being a little sloppy with my work here. Right. Engineering kind of sloppy, putting e's there and there now. Here, the e and the ln cancel, leaving you with the absolute value of y over L minus y. Can I get rid of the absolute value signs? Well, people do, and it gets the right answer. So we will. Why bother with the absolute value signs in the first place? Kind of just to remind you that in theory they should be there. But you end up getting the right answer anyway, even if you get rid of the absolute value signs. And I'm going to think of e to the c1 as being, say, c2. And now bringing this stuff over here. And again, my goal is to solve for y. Still not quite there yet. Multiply both sides by L minus y. Get this. Should I combine the C2 and the L to get C3? Probably not, because the C2 is in 2 spots for one thing. And another thing is I probably want to keep the L in there as is, because it is the carrying capacity. It is relevant for thinking about the model. Just keep solving for y. It's on 2 sides here, so I better now add this to both sides and then factor out what I can, factor out the y, in fact. So I'm doing 2 steps here at once. I added C2y e to the kt to both sides, canceling it on the right and bringing it over to the left. And then on the left, I have 2 expressions that involve y, then where the y can be factored out, and I'd get this. Almost done, right? Now just divide both sides by this. Divide both sides. Y equals C2L e to the kt divided by 1 plus C2 e to the kt. Is this a general solution? Yes. It's not typically the way people write the general solution, though. What's the more typical way people write the general solution? I'm going to now multiply the top and the bottom by, well, or divide the top and the bottom by C2 e to the kt. Same as multiplying the top and the bottom by C2 inverse e to the negative kt. If I do it to the top, I got to do it to the bottom because so that I multiply by a big 1. To isolate the L on the top, right? Because the C2 and the e to the KT will cancel. And on the bottom, it's going to completely cancel with this thing. This part's going to become a 1 right there after multiplication. And the C2 inverse e to the negative KT times 1 is itself. I'm going to now write that as C e to the negative KT, where C is really C2 inverse. That's a more typical way people write a general solution. However, it does suffer from a defect. Same defect that we saw in an example last week, in that it doesn't include every possible solution. It misses one solution. It misses the equilibrium solution at y equals 0. Not only is y equals L, that horizontal line in equilibrium solution, but also y equals 0 is as well, because it makes that 0. And that makes sense with the population. If there's no fish to start with, and you're not allowing fish to be imported, then there will continue to be no fish. So even though this misses it, it's still the most common way to write it, the general solution. You should be able to check. And remember the final exam is going to be take home, but you won't be doing everything by technology. You should be able to do some things by hand. You should be able to check that this really does work. Check that it solves the differential equation. The left-hand side of the differential equation, LHS, is dy dt. LHS means left-hand side. Actually, in Calc 1 right now, we're doing Riemann sums, and LHS there means left-hand sum. But now, for you guys, it means left-hand side of the differential equation. Find the derivative of this thing, I guess, with the quotient rule. Low d high is going to be 0, because the derivative of L is 0, minus high d low. And the chain rule is going to give that for the derivative of the bottom, divided by the square of what's below. That's the quotient rule. Can be simplified a little bit to this. And what about the right-hand side of the differential equation? That's ky times 1 minus y over L. Substitute this function in place of y and simplify. We should get the same final answer. It's not obvious that that's going to happen, is it? Substitute this function. Do notice in the y over L term, the L's will cancel. Right? With y over L, I cancel the L there with this L there. When I substitute the function in place of y right there. I guess subtract, do the subtraction here, so get a common denominator of this thing. And yeah, now I'm starting to see how this is going to come together. The ones cancel. And yes, now if you multiply this times that and times k, you will get the same final thing. Amazing. I'd be scared that I was going to make a mistake in this, except I've done this example so many times in many classes over the years that I'm pretty confident I can do it without a mistake. So we have a match. We are happy. It does solve the differential equation. As a general solution, remember what that means, typically at least. It means, for one thing, this will be a solution no matter what C is, and it is. We just checked that. Usually what it means is all other solutions can be written like this. That doesn't quite happen here because, again, it misses the equilibrium solution at y equals 0. There's no value of C that will make this 0. There is a value of C2 that makes that 0. That's C2 is 0. So evidently the problem is coming in the fact that we are simplifying it in this way by letting C equal C2 inverse. Okay, we live with it. How about, can we write a formula for the unique solution of the generic IVP? Pretend y naught here is a fixed constant, not an arbitrary constant, although it is arbitrary because I'm not saying what it is. But I'm thinking of it as fixed is the key thing. Can I solve for the C that'll make this work? Is the question. I'm plugging in t equals 0 into the solution function. That's what I just did. E to the 0 is 1, so this simplifies to L over 1 plus C. Can I solve for C in terms of y naught? Sure, why not? Multiply both sides by 1 plus C. It's trying to solve for C. It's trying to solve for C. Subtract y naught from both sides. Divide both sides by y naught. And this looks like it's C. So the unique solution of the initial value problem using the phi notation for the function name and the subscript to emphasize the initial condition can be written as L over 1 plus C is this times e to the negative kt. But then I'm back to fractions within fractions. So let's simplify by multiplying by y naught over y naught. Y naught times L over y naught plus L minus y naught e to the negative kt. And this is my favorite formula for the solution because now we're back to including the equilibrium solution. Y naught is 0, does make that always 0. What fun. It's like we went in circles there. This is the unique solution of the IVP. Let's confirm that with Mathematica. I like using dsolve value the best, even though you have to do a little extra typing with the word value. Differential equation, y prime of t equals, don't forget to do double equal signs. Not saying what k is, that's okay. K times y, make sure to put y of t in there though. With Mathematica, it needs to know y is a function of t. 1 minus y of t over L. Initial condition, y of 0 equals y naught. Not bothering with the subscript. Then outside that list, put a comma, y of t, comma t. We may have to expand it, but let's see what it produces. Okay, don't have to bother expanding. This looks the same as what we've got there, except the e to the kt is playing a different role. You can get from the Mathematica answer to my answer here by dividing the top and the bottom by e to the kt. Canceling completely on the top, and in the bottom, you'd have L times y naught times e to the negative kt, like I do. And the e to the kt here would cancel, leaving you with just y naught, like I do. So that does confirm that we have the right answer with Mathematica. Okay, let's think about what solutions look like now. What do the graphs of these things look like? Of course, I could get Mathematica to graph them for me for particular y naughts and particular L's. But let's, instead of doing that, let's think about the general situation here. And let's in fact see that we could use the differential equation to figure out what solutions look like without having actually solved for solutions. We could do that. That right-hand side doesn't depend on t. It's a function of y. It's an autonomous equation. The slope field is going to have slope marks whose slopes are constant along horizontal lines where y is constant. Solutions are going to be horizontal translations of each other. It's not a pure antiderivative problem. We had to separate variables before we integrated. So solutions are not vertical translations of each other, they're horizontal translations of each other. And in fact, if you graph this function f of y here, it's helpful for helping you think about the slope field. That's a quadratic function of y. F of y is ky times 1 minus y over L is a quadratic function of y. If you expand it out and rearrange, you'll get negative k over Ly squared plus ky. You could graph this as a function of y, and it's a helpful thing to do to think about the slope field. What I'm about to draw is not the slope field itself, but just a graph of this function that will help me draw the slope field. Quadratic, negative coefficient of y squared. The graph's going to be an upside down parabola. Roots are at 0 and L on this horizontal axis, which I'm labeling with a y. Don't let it mess with your brain that y is horizontal in this picture, whereas it's vertical in the slope field. It's okay. Upside down parabola, looking like kind of like this. This does kind of now feel similar to what we did with the discrete model, where we made the cobweb plots, but we're not going to do that here. This is maximized, by the way, at L over 2. That's where the derivative of this function equals 0, but I won't bother verifying that. This can help me draw the slope field. This is a tool to sketch slope field in a plane where t is horizontal and y is vertical. There are two equilibrium solutions, y equals 0 and y equals L. In the slope field, those are horizontal lines that represent constant functions that solve the differential equation, because they make this function f of y, the right-hand side function of the differential equation, equal to 0. And derivatives of constant functions are always 0. That's why these solve the differential equation. And the formula that we got right there, if y naught is 0, this function's always 0, right? And if y naught is L, this function's always L. Because if y naught's L, you get a 0 there. You get L times L there divided by L there. L squared divided by L is always L, assuming L is positive. Not 0. You don't want a 0 carry. So, yeah, that constant function is an equilibrium solution as well. These equilibrium solutions in the slope field correspond to intercepts of this graph of the function on the right-hand side of the differential equation. I can make that graph, obviously, without thinking about differential equations at all. What I'm doing here is I'm using it to help me think about the slope field for the differential equation. Moreover, I can think about what slopes are like in other places in this slope, this plane here. If y is bigger than L, if I think about solutions up here, the slope field has negative slopes because f of y is negative when y is bigger than L. This part of the graph is below the axis. F of y is negative, so the slope marks I make up here must be negative. Close to 0 if you're just barely bigger than L, but getting further from 0 as you move away from L. But notice I'm trying to make these constant slopes along horizontal lines. And that means solutions up there have to be decreasing functions. right? Because those slopes are negative. And the solutions have to follow the slope field. Anytime you pass through a midpoint in one of those line segments, it's got to be a tangent line to the curve. Same kind of thing happens if, and that makes sense intuitively, if there's more fish in the lake than the carrying capacity, you're going to have a die-off. Won't be enough food. More fish will die than be born. And it seems intuitive that you're probably going to approach this carrying capacity asymptotically instead of overshooting it. Because of uniqueness of solutions, actually, these graphs can't touch each other. They approach each other, but they can't touch. If y starts out negative, well, that corresponds to negative fish. But if we ignore the fact that we can't have negative fish, we can still draw the slope field. When y is negative, f of y is also negative. So we're going to get negative slopes in here as well. And they get more negative the further y gets below 0. So solutions are going to decrease over there as well, like this. In between is where the more interesting and important stuff happens, and that's where the right-hand side is positive in value. So your slopes are going to be positive, and in fact, most positive at L/2. That's where the slope marks are going to have the highest positive slopes, and then they're going to be closer to 0 as you get close to L or close to 0. Some intermediate slopes in here. And solutions are going to look like this. And that's pretty intuitive that this would happen. This would be what you would predict, even if you never thought about it in terms of differential equations. You got kind of exponential growth in this range here, but then this growth has got to level off toward a rate of change of 0. So the population approaches the carrying capacity, again, without overshooting it. Now, in real life, can you overshoot carrying capacities? Yes, it can happen, right? Real life has got some randomness involved, and so it's not as deterministic as this. But it still might be a helpful model. In fact, people do use the logistic model to model things like fish populations and even the population of people in the entire world. People try to use a logistic model to predict what the carrying capacity of the world is. Did you know that? For people. What have they predicted? I don't remember offhand. How do they predict it? How do they use this? They gather data about the world population over the last, say, 200 years, and they try to fit a logistic kind of curve to that and see where it looks like it's going to level off. Does that mean they're right? No. It's just what the data indicates based on this model. Of course, it's just a model. It's overly simplistic, but people hope it does good enough is the idea. So this is a tool to sketch the slope field. I do want to talk about Euler's method in a few minutes here, but before we do, I want to notice something else. In this formula for the solution phi sub y0 of t, depending on the value of y0, this function may or may not have a vertical asymptote. This is relevant for our discussion about existence and uniqueness, which we'll come back to more on Thursday. If y0, the initial population, is larger than L, I claim that this graph, this red graph that I drew here, has got a vertical asymptote for some negative value t. And if y0 is negative, there's a vertical asymptote for some positive value t. Now, that's not, again, really relevant for fish, but mathematically, it happens. But for the y0s between 0 and L, these graphs don't look like they have vertical asymptotes, and in fact, they don't. Can that be seen symbolically? Yeah, figure out where the bottom's 0. what values of t will make the bottom 0 where you're dividing by 0? And maybe it will depend on what y0 is. If I set the bottom of the formula, which is this expression, equal to 0 and try to solve for t, what happens? It's supposed to be a y0 there. I guess I'd have to first subtract y0 from both sides. And then divide both sides by L minus y0. And maybe then I want to also get rid of the minus sign on the right by changing the order of the y0 and the L on the bottom. Trying to solve for t, now take the natural log of both sides. Divide both sides by k, which is assumed to be a positive number. Looks like that's the value t where a vertical asymptote will occur. If what? If the input to the logarithm function is positive, right? The natural log here, when we're thinking about just pure real number math, no complex numbers, the natural log has a domain that's only includes positive numbers. So in order for this to exist as a real value t that's going to give you a vertical asymptote to your solution, y0 over y0 minus L must be positive. What's that condition equivalent to? That's equivalent to y0 and y0 minus L having the same sign. Y0 and I'll say it that way. Y0 and y0 minus L having the same sign. So I'm solving this by writing words here. I don't really want to multiply both sides by y0 minus L because that could switch the direction of the inequality depending on the sign of that thing. And y0 and y0 minus L are going to have the same sign in one case when y0 is negative. They'll both be negative. And in another case where y0 is bigger than L, then they'll both be positive. If y0 is between 0 and L, then one's positive, one's negative, right? If y0 is between 0 and L, this is positive, this is negative. Question? L is positive. I'm not saying, I'm thinking purely mathematically here. I'm not thinking about the application. I'm saying if these two quantities have the same sign, then this fraction will be positive. That's all I'm saying. They have the same sign in two cases. This is equivalent to either y0 being less than 0, in which case both of these quantities that I circled are negative, or y0 being bigger than L, in which case both of these are positive. If y0 is between 0 and L, then this is positive and this is negative, and this fraction would be negative. So I can't plug it into the logarithm function. So what I'm trying to say is, this is the condition when you're going to have vertical asymptotes, just like I said a few minutes ago. And those vertical asymptotes are going to occur here. And then the claim here is when y0 is bigger than L, that's a negative number. And when y0 is negative, it's a positive number. Is that obvious? When y0 is negative, this fraction will be positive. Let's just try an example. Like if y0 is, just to make something up here, -5 and L is -10, this fraction is going to be positive 1/3, and the logarithm of it's going to be negative. Multiply it by -1 over k, you get a positive number. When y0 is negative, your vertical asymptote is at a positive value of t. And when y0 is bigger than L, evidently, this quantity is a positive number, or bigger than 1, in fact. Yeah, that makes sense. Like if y0 was 5 and L was, or if y0 was 15 and L is 10, 15 over 15 minus 10. Yeah, that's bigger than 1. ln is something bigger than 1. It's positive times a negative number is negative. You got a negative value of t where your glass asymptote occurs over here. This is a worthwhile discussion because, again, it reemphasizes the fact that for some differential equations, some solutions can blow up in finite time. This blows up in a finite positive time if you let t run forward. This blows up in a finite negative time if you let time run backwards. Wait a minute. When would I ever let time run backwards? Not in real life, but in the math, I could let time run backwards. Right? You can do anything in math. You can even go faster than the speed of light in math, right? I can do anything in math. I'm limited by physical reality in physics, but in math, I can do anything. I can let time run backwards in my mind, my imagination. Well, why did that happen? In a nutshell, it's because we got a function on the right-hand side that's nonlinear in y. And so, as a little hint, we'll come back to this a little on Thursday, it's not satisfying a Lipschitz condition in y. You weren't here. That's the man with the unfortunate name.
I know, I saw
you saw the video, okay. It's not satisfying a Lipschitz condition in y because of the y squared. So it's relevant for that discussion. It's good to see examples, right? And not just think theory. Hey, we want to remember this example for Thursday. All right, so we'll do more theory on Thursday. What about Euler's method? I did, in our overtime session on last Thursday, talk about Euler's method. Geometrically, intuitively, but let's be a bit more formal about it now. And I'll go ahead and use the book's notation now. So you got a differential equation, a first order ordinary differential equation, initial value problem. ODE means ordinary differential equation. IVP means initial value problem. dy dt equals f of ty, y of 0 equals, okay, I got to change to the book's notation, sorry. Y of a equals alpha is the book's notation. Sorry. Almost always a is 0, but we'll allow for a general a. The alpha, however, is not always 0. I would actually be more prone to use this kind of notation. Y of t naught equals y naught would be more common notation that I personally would use there. But trying to be consistent with the book here. Euler's method is a recursive method. We are iterating a function effectively to get a list of numbers. We're also given, or we choose, a step size, which we could call delta t, and some books call delta t, but we're going to call it h to be consistent with the book. That's a common thing we've used for step size in the past as well. Here's the method. Euler's method. Set W naught equal to alpha. And W sub I plus 1 equal to W sub I plus F of T sub I, comma, W sub I times H. That's Euler's method. You use this recursive equation now for I equal to 0, 1, 2, 3, etc. Yes, that does include 0, by the way, on the subscripts here, because when I is 0, we'd be finding W sub 1 using W sub 0. So we talked about the idea of this with an example last Thursday. Let me draw a generic picture. Here's your TY plane in which you've got the slope field drawn, say. You got a particular starting value of time, call it alpha. Almost always alpha is 0, but I'm drawing it as if it's non-zero here. Excuse me, that's A, sorry. A. Alpha is the starting value of y. So there's your initial condition with coordinates A comma alpha, or if you prefer, T naught comma Y naught. We use the little slope mark centered at this point that's got slope equal to f of t comma y at that point, which would be f of a comma alpha, which is the same as f of a comma y w naught, because w naught equals alpha. We follow that line forward in time by h units to get to the point we could call it a t naught as well. To get to the point, say t1 equals a plus h. And the coordinates of this point right there are going to be t1 comma w1. Why? Because we took the old value of y, w naught, which is the same as alpha, and we added on a change in w along this line. Call this delta w if you like. And that change in w comes from thinking of the derivative as a rate of change. Slope times the change in t gives you the change in w along that line. Another way to think of that is the slope is the ratio, rise over run, delta w over h. This distance right there is h. So delta w is f of t naught comma w naught times h. We hope that if h is small enough, that this line is not only tangent to the solution, which it has to be, but is close to the solution, if h is small enough. This green graph that I'm drawing here is supposed to be the true solution. So its coordinates at this point would be t1 comma, well, the book writes it as y of t1, where y of t is your unique solution. I would be more prone to write that as t1 comma phi sub alpha of t1, using an alpha because that's the same as y naught. These are all the same. The book uses alpha as the initial value of y. I often use y naught, so that's why I have a y naught there. W naught, by definition, in Euler's method is the same value. So if I use my solution function formula notation with the phi as the function name and the subscript giving you the initial value of y, I would put an alpha there, and this would be evaluated at t1. That's just the first step of Euler's method. The next step is to do it again. But the errors in Euler's method do kind of compound because, well, yes, you're making an Euler an error in your approximation in the first step because you're using the tangent line to approximate a curve. But the error in the second step includes not only that kind of error, but also the fact that you're using a different point, not on the curve. But you do it anyway, because what else can you do? So now you use the slope at this point. and follow it forward in time by h units of time. To get to T2 is a plus 2h, and find the coordinates of that point in the same kind of way we found the coordinates of this point there. The coordinates of this point will be T2 comma W2, and W2 is going to be W1 plus f of T1 comma W1 times h. The change in W is that now. Once again, I'm really using the fact that the derivative, the slope of this line, which is the function f, its value at this point, multiplying that slope times the change in t to estimate the change in W, to give you the exact change in the line, that's the delta W there, which approximates the change in the true solution. But again, the true solution is continuing to go on its merry way here, maybe continuing to be concave up, and the error might be even bigger now, most likely. Okay, and then you iterate, you keep going. Let's implement this now. How about for our example, our logistic model example? Though if we're going to do that, I should pick a value of k and a value of L. For simplicity, we'll choose L to be 1. Maybe that represents 1 million fish, if L is 1. If your units of fish are in millions, that would represent 1 million fish. What should I choose for K? K is essentially the continuous growth rate when the population is small. You know, population growth rates for people in the world like 1%. For fish in a lake, if the population is small, they probably grow faster. I don't know, 5%, 10%, who knows? Let's pretend it's 10%. So this would be your model if K is 0.1 and L is 1. This would be my f of y. What initial condition? If the units are in millions and I want to start small, I want a number less than 1 here, close to 0. I could choose 0.1, but maybe 0.01 million fish, which would then represent 10,000 fish. Small relative to the carrying capacity of 1 million fish. So let's try to implement Euler's method by hand. It's nice to organize your work in a table. Give the value of I for the first column, the value of Ti for the next column, the values of time, the value of Wi, and it's also nice, I think, to put a column for the value of f of Ti times Wi times h. Then I'm going to add to the Wi to get Wi plus 1. What do I choose for h? That's up to you. Time is in years. I don't know, we could choose h as 0.2 just to be something different here. 0.2 years, so that would be like about 72 days, 73 days. So the TIs keep going up by 2.2. The initial value of Wi is the initial population. That would be 0.01. Here I would need to figure out f of 0, 0.01 times h is 0.2. Well, careful. For our example, this is just f of Wi, because f doesn't depend on t for this example. So I really need to only think about the 0.01 here. Plug in 0.01 into this expression to get 0.1 times 0.01 times 1 minus 0.01 times h. This, of course, is 0.99. 0.1 times 0.01 times 0.99. The function value is that 0.00099 times 0.2. In ordinary decimal form, this would be 0.000198. That would be your approximation for how many new fish grew, how much the fish population grew during the first 1/5 of a year, a little more than 2 months. In millions, what would this be? This was 10,000, I guess 198 fish. That makes sense. Better double check that. Times 1 million. Yeah, 198 fish. 200 babies were born and 2 fish died. Okay. So add this to the previous population, 0.01, to get the new population. 0.010198, I guess. Keep going. F of 0.2 comma 0.010198 times 0.2. Again, with our example, the 0.2 right there is irrelevant. I'm just plugging that thing into this function. 0.1 times 0.010198 times 1 minus 0.010198 times 0.2. Yeah. I'm already tired of doing this by hand. It's not going to be too much different. It's going to be maybe a little bit bigger, maybe 199 fish, maybe 200 fish. I don't know. We'll see. I'm afraid of doing that one in my head. Okay, about 202 fish. 0.000200188. About 202 more fish. Add that to the preceding amount here. Because the next value of W, 0.0103998. So we started with 10,000 fish, then went up to 10,198 fish, and then went up to approximately 10,400 fish. Keep going. Obviously, this is better to implement with technology. Let's try it with a spreadsheet and then Mathematica. And then we'll be done for the day, ending at 1:30. Just 2 minutes ago there, my brain went there. My brain thought, oh, I got till 1:40. So spreadsheet. For this example, my f of y function, I'll just type it as f of y. 0.1 times y times 1 minus y, just for reference sake. I'm using y of 0 equals 0.01 and h equals 0.2, which I think I'll put here in cell B2 as a number. And I'll put the 0.01 here in cell B3 as a number. I guess this is in B4. Okay, make your table I, Ti, Wi, f of Ti, well, f of Wi times h. And do your typical kind of thing here with the I column, start at 0 and keep going up by 1. How far out in time do we want to predict? Well, let's try 5 years. So h is 0.2. We got to go 5 steps per year. So 25 steps. One more. Ti starts at 0. Wi starts at What's in cell B3? To program this to allow yourself to change the H and the initial condition, it's good to use the cell references. I will have to type the function in here effectively. Like this. H is in B4, use $signs to copy and paste correctly. Does that look good? 0.1 times the C7 is the value of W. That's what's going into the function. B4 is the H. Gets multiplied on the outside with a $sign. For this one, it would be TI plus H, which is in cell B4, use $signs. So TI is going to go up by 0.2 every time. Here's the key. Well, you could argue this is the key one and this is the key one. They're all key, I guess, but take this one and add that one. Right? The previous value of W plus the change in W. Now just copy and paste. Click and drag. Does that match what we got by hand? Yes, that does. So according to this model, we're predicting a population of about 16,304 fish 5 years from now. Is that what the answer really is? Let's compare with the exact formula in Mathematica. I can take this as a shortcut. I can take this expression and do slash dot in curly braces, y0 arrow 0.01, L arrow 1, K arrow 0.1. Oh, and I got to do T. T arrow 5 years. 0.1638. Where'd my spreadsheet go? 0.16. Yeah, 16,304 compared to 16,381. Not too far off. This one's a little higher because the graph's concave up, so the tangent lines are underneath it. They're underestimating the true value. Can Euler's method be implemented in Mathematica? Yes, it can be, very quickly, actually. Define your right-hand side function. I'll use a y. And use, well, do something else. This one's a little funny. I'm going to call it EM, curly braces, T underscore W underscore. This is going to be a function that takes two-dimensional input and gives a two-dimensional output. T gets updated by 0.2 every time. I'm adding 0.2 to T. And W gets updated by F of TW times 0.2. This is Euler's method right there. No subscripts, but that's the idea. Enter that, and I'm calling it EM because it stands for Euler's method. And then use nest list to iterate that function EM. Initial condition 0, 0.01. You have 5 years into the future with 0.2 for H. I need 25 steps. Oh, and what's going on here? Why is that having a problem? Oh, I know what the problem is. Sorry, abort that. Problem is I need F of W there. There we go. There we go. Same thing we got with the spreadsheet, right? 16,304. Compare that with the spreadsheet. So I'm iterating this two-dimensional function, so to speak, updating both the value of T and the value of W every time.